In the previous lecture, we started to see how the wave function for the system that we are trying to look at can be expressed. We expressed it as a superposition of states from an orthonormal basis set. And from here, we extended it to the understanding how an measurable could be obtained by getting the expectation value. Here, we were able to understand where if you get a product between the projection and the operator that you want to observe, the trace between these two, product of these two matrices gives you the observable. But of course, we discussed this only for the pure state, where this projection operator was given as follows. And the given element for this operator will be given as this. When we moved on to ensemble averaging, we understood that it's all the same, where instead of the projection operator, we now define the density matrix. This is where we finished off the previous lecture. So what we have effectively done is that to understand the wave function has two components, the coefficient and the state. Since in NMR the state doesn't change, all the time dependence can be encoded within the complex coefficients. And slowly you are able to understand that the projection operator has these coefficients in it, where for a given spin state, matrices can be determined for the operator that you want to observe. So this makes our job easy, where if we are able to get the projection operator, or in reality the density matrix, and take the product with any of the observable you want to have, you will know what is the outcome of a given experiment. Most importantly, that takes us to the case of how can we understand the time evolution of the density matrix, which is what will form the core for this lecture. So let's write the time dependent Schrödinger's equation, which is given by IH cross d psi over dt is given by h psi. The thing that you're able to understand here, the time evolution of the wave function is given by this equation. So similarly, if we are able to get the time evolution of the density matrix, then we will be able to understand how does the density matrix behave at any time. And after a given time, let's say you want to observe it, you take the product of the observable operator with that of the density matrix, you will be able to get the final answer. So in order to do this, let's try to compute this following element of the density matrix. This is taken just for the sake of simplicity. Here, what you are able to understand is that this is nothing but sigma km, which will be given by the differential of cm star ck. Remember, you are in density matrix, so you need to have an over bar. So therefore, this will be dcm star over dt times ck plus cm star dck over dt. So what is this? This is nothing but d sigma over dt. So all we need to know is how do the coefficients change the function of time, which can be obtained from the time dependent Schrödinger's equation. So let me write the Schrödinger's equation here. Instead of writing in psi, I am going to be writing it as a summation, as we have seen earlier here. This will be given by summation Cn over n h on ket n. Since all the time dependence rests on the coefficients and not on the states, the time differential will only act on this. So similarly, the Hamiltonian only will act on the states, so therefore Cn can come out. So in order to determine what will be the time differential of this given coefficient, why don't we pre-multiply it with the bra of k and integrate it over space in order to find what will be the coefficient. So therefore the LHS becomes sigma Cn with summation over n bra k ket n equal to summation over n Cn bra k Hamiltonian ket n. Since you are talking about an orthonormal basis set, only when k is equal to n, you are going to have a non-zero entity on the left hand side. So therefore this is going to become IH cross dck over dt will be given by summation over n Cn k Hamiltonian n. This can also be written as hkn. And therefore what we are able to understand, the time coefficients that we want are actually present here and can be therefore deduced. So just changing the indices, what will be dcm star by dt will be the complex conjugate of what you got, so it will be minus IH cross, minus comes because of complex conjugation, summation over n Cn star, and then when you take a complex conjugate of KHN, it's going to be NHK, but remember we have to replace K with an M, therefore it is going to be NHM that you got. Let's try to go from here. Let me rewrite this equation for the sake of simplicity. D sigma over dt, and the dck over dt is given here, dcm star over dt is given here. Let's try to incorporate it. If you take it on the right hand side, you are going to get 1 by minus IH cross times summation over n Cn star n Hamiltonian m. Once again, you take it on that side, 1 over IH cross summation Cn k Hamiltonian n. Of course, I missed the ck here, that comes from this term, and I also missed the Cm star. Of course, these are over bars because you are having an ensemble average. You are able to appreciate the fact these coefficients can now be represented in form of the density matrix summation over n. Whenever you have the n and the k, you have k sigma n times n Hamiltonian m. I'm going to take the minus IH cross, 1 over IH cross outside, so it will give me minus summation over n. Cm star Cn is n sigma m times k Hamiltonian m. So all that we have done is to change the coefficients into the density matrix form. And also we'll do one more simple manipulation. Since these are numbers, you can push one to one side, the other to the other side. So this can be written as sigma n k Hamiltonian n times n sigma m. If you carefully pay attention, you are able to understand that this term, which is sigma n over n ket over bra n, will be equal to 1, which we had seen earlier. So therefore, this will get reduced to, I am also taking a multiplying dividing by I, so therefore you are going to have I by minus I square will be plus 1, I by h cross, the whole divided by so this will be equal to, I am also multiplying the whole equation by I, so you are going to have I by minus I square, which will be plus 1 divided by h cross times, and these terms have vanished because of the integral, so you are going to have k sigma times Hamiltonian times m. So similarly, you are also able to appreciate the same term exists here, so that will also go to 1 minus bra k Hamiltonian sigma times m. Once again, the states on the left hand side and the right hand side are same, so therefore this can be written as I divided by h cross times bra k sigma Hamiltonian minus Hamiltonian sigma times m. And immediately you are able to understand this is nothing but the commutator of sigma comma Hamiltonian. So therefore this will get written as I by h cross sigma by Hamiltonian. Generally this expression is given as minus I times Hamiltonian comma sigma. This is an important inference that we have come to, that is, the change of the density matrix as a function of time is given by I times Hamiltonian comma sigma, the commutator between the density matrix and the Hamiltonian. Generally we set h bar to 1, which is why I am not pronouncing h bar out. This is a differential equation. The solution for this equation, when the Hamiltonian is time independent, would be given by sigma of t will be equal to exp minus I Hamiltonian t times sigma 0 times exp I Hamiltonian t. So what we are able to understand is that in conditions where you have a time independent Hamiltonian and you know the initial density matrix, you can actually tell what is the final density matrix. Therefore, if you are able to get the final density matrix, let's say you want to observe Ix, you just take the product between Ix and sigma and find what is the trace, you would be able to find what will be the outcome of your given experiment. And of course, all this is under the pretext that your Hamiltonian is time independent. Luckily, you have a simplification of what you end up getting. For any operator exp of A, it can be given by the Taylor series expansion of 1 plus A by A square by 2 factorial plus A cube by 3 factorial and so on. So you have an operator here which is of the form of minus IHT. So this is given by the Baker-Campbell-Hausdorff formula. In short, the BCH formula. So when you have something of this sort, then sigma of t would be given by sigma of 0 minus it by 1 factorial Hamiltonian comma sigma of 0 plus it square by 2 factorial Hamiltonian double commutator with respect to the Hamiltonian with the operator that you have minus it the whole cube by 3 factorial Hamiltonian comma although this BCH formula seems tedious, we will see cases where when we take a certain density matrix to start with, how does it evolve as a function of time with a given Hamiltonian. Okay, but remember this solution is only when the Hamiltonian is time independent. The next class we will understand if the Hamiltonian is time independent, how this formula could still be exploited to understand how the density matrix changes the function of time. So why are we worried about the density matrix is largely because this consists of the information which has the complex coefficients that are time dependent, and the moment you find what is the density matrix, you should be able to take the product of the density matrix with the operator you want to observe with, and finding trace would help you find whatever it is. Therefore, if you get density matrix at any time, you can actually tell what is that you're going to observe. The next class we will see how when the Hamiltonian is time dependent, the same formula can be exploited.